Okay, so the plan for today's class is to cover sections 13.1 and 13.2. I'm going to leave space curves that's a part of 13.1 for the supplement, just to make sure that we get through all of the important material in 13.1 and 13.2. And then the supplement will also cover 13.3 and 13.4. So we're going to cover the first half of chapter 13 today, and then the second half in a supplement. I know it's a bit of a strange week because we had Memorial Day off on Monday, and then I didn't want to post a supplement on 13.1 and 13.2 yesterday because then if we just started into say 13.3 or 13.4 today, for folks who didn't have a chance to turn that around and watch that 13.1 and 13.2 supplement, it would be a little bit difficult to keep track, so to keep caught up. So that's why I decided to do it this way. This puts a little more of the work toward the end of the week, unfortunately, but having that Monday off, throws a little bit of a wrench into things. But from this point forward for the next probably 3 weeks or so until Juneteenth, I think that's also on a Monday, but for the next few weeks, we should have pretty consistent Monday, Wednesday classes. And then typically I'll post a supplement on Tuesday and on Thursday to go along with those class meetings. Okay, so chapter 13 is all about vector functions. And briefly, what is a vector function? Well, it's a function with domain real numbers. In our course, we're focusing just on real numbers. We could say the same thing with complex numbers, but for our purposes, it's a function with domain real numbers and range some multidimensional space. So this could be R2, this could be R3, this could be a two-dimensional space, a three-dimensional space. It could even be a higher dimensional space, but we're primarily concerned with the case n equals 3. So we're thinking of taking one variable as input and then getting an output that is an ordered set of three variables. So we might write this in a different notation as saying the function f, which we're writing in bold now because we're thinking of it as a vector, the function f takes r to r3. And again, this function f, this should be bold. I don't know why. Sometimes OneNote loses my my like bold or indentation or some of that. Doesn't seem to happen in Word as much, but anyway, the function f, the vector function f, has one input and three outputs. So let's look at an example. Pretty straightforward idea, but let's go through an example just to drive the point home. We have a function f of t that's a vector valued function. So f is written in bold because it's representing a vector. And that function is represented by the vector with three components, where each component is a real valued function. Each component individually, say this first component here, takes one real number as input and gives one real number as output. The same can be said of the second component and the third component. And we want to evaluate this function for the input t equals 3. So in other words, we want to know what is f of 3. And because f is a vector, I'll write it with a little vector arrow over top when I write it by hand. So we want to know what is f of 3. Simple enough. This is the vector with three components, the first of which is 3 times 3, the second of which is e to the 2 times 3, and the third component, sine of 3. Or if we simplify that a little bit, we get 9 comma e to the 6th power comma sine of 3. So f takes as an input a real number, for instance 3, and gives us an output a vector, for instance this vector of that has these three numbers as components. This is a vector with three real numbers in each of its components. So an important note, a vector function that has one input and multiple outputs, this is a fundamentally different concept from a multivariable function. Even though it might kind of, the descriptors might kind of sound like they're talking about the same thing, a multivariable function, or what's often called a function of several variables, that's the situation where we have multiple inputs and one output. These are fundamentally different ideas, and it's very important to realize that. When we're saying a vector function, we're talking about one variable as input, multiple variables as output. When we're talking about a multivariable function or a function of several variables, we're really talking about multiple inputs and one output. And again, at first glance, you might say, well, kind of what's the difference, whether I have a real number input and a vector output, or essentially a vector input and a real number output? Well, there's quite a big difference. We'll start looking at such functions in chapter 14, the next chapter. But just as a quick example of a multivariable function, again, not a vector function, not what we're talking about here, but to give an example so you can see the difference, we could have a function. Note that this f is not bold because it's representing a scalar, it's representing an output that's just a real number. Takes as input multiple variables, in this case, maybe x, y, and z, and it gives an output that's some combination of those variables, in this case, x plus y minus z. So for instance, f evaluated at 1, 2, 3, where x equals 1, y equals 2, z equals 3, would be 1 plus 2 minus 3, or 0, a real number. That's what we mean when we say a multivariable function. In this chapter, we are only talking about vector functions, one input and multiple outputs. And again, in chapter 14, we'll start looking at examples like this. So you might have in another course seen the idea, say, of partial derivatives or something like that. Well, that's an idea that applies to these functions, not to the vector functions that we're talking about. Important to keep those two ideas separate in your head. What we're talking about here in chapter 13, we have one variable as the input, multiple as the output. A second note is that the things from Calc 1 and 2 that we studied, such as limits, continuity, derivatives, and integrals in particular, when these are applied to vector functions, they essentially work just like they did in Calc 1 and 2 on a component-by-component basis. So the kind of TLDR of much of chapter 13 is we're kind of just doing Calc 1 and 2, but just doing it 3 times for each problem. Obviously, that's a bit of an oversimplification, but you can kind of think that way a bit in this chapter. So with that in mind, with this second note in mind, that limits, derivatives, and integrals of vector functions get performed component-wise in the same way that they were performed on real-valued functions in Calc 1 and 2, let's take a look at this next example. So example 2, for the following vector function f, compute the indicated quantities. Here our vector function is the same as above. F of t equals 3t for the first component, e to the 2t for the second component, and sine of t for the third component. So let's compute a limit. Remember, there is one input and multiple outputs. So when we're talking about a limit, we're just saying, what does that one input go to? So limit as t goes to 2, f of t equals what? Well, the limit is just performed component-wise, as we mentioned above. So we could think of this as just limit t goes to 2 of 3t in the first component. In the second component, limit as t goes to 2 of e to the 2t. And in the third component, limit as t goes to 2 sine of t. Let me get myself a little more space here. So again, it's just kind of like the limit passes through the vector brackets in some kind of loose sense. And then, of course, we can evaluate each of these limits. We know that in the one-dimensional sense, each of these are continuous functions. So the limit of that function is just the function evaluated at the limiting point, or it's 3 times 2 is 6. E to the 2 times 2 is e to the 4. And sine of 2. And of course, note that this is f evaluated at the limiting point 2. So again, even continuity works very similarly, right? Each of the component functions is continuous. So continuous on the whole real line in this case, but certainly continuous at 2. So the limit t goes to 2 f of t equals f of 2. So we can kind of evaluate the continuity of the whole function by evaluating the continuity of each of its component functions. Okay, what about derivatives and integrals? Well, let's take a look at this next part of this example. For the same function, let's compute f prime of t. In other words, let's compute d by dt f of t, just to be a little more explicit about the fact that we're differentiating with respect to the variable t here. So what is f prime of t then? The derivative of this vector function or vector valued function. Again, it's just the derivative of each component, right? So the first component is the derivative of the first component of f. The first component of the derivative is the derivative of the first component of the original function. So it's the derivative of 3t, which is just 3. The derivative of the second component, e to the 2t, is going to be 2 e to the 2t. Don't forget the chain rule. And the derivative of sine t is cos t. This is a new vector value function. You know, we could think of it as some g of t or something. It's a new vector valued function that represents the derivative of the original one. How do higher derivatives work? Well, again, just like in Calc 1, if we wanted to find the second derivative of f, we would just differentiate the first derivative being a function, a vector function in and of itself. Its differentiation will work the same way, and so on, right? What's f prime at 2? F prime at t equals 2. Just like in Calc 1, we take the derivative kind of symbolically, we take the derivative in general, and then we plug in t equals 2. So here we have our derivative, f prime of t here, and we plug in t equals 2. That doesn't affect the first component, it's just 3. The second component becomes 2 times e to the 2 times 2, or 2 times e to the 4th power, and the third component, cosine of 2. So again, pretty straightforward. We basically just do Calc 1, but 3 times. Once for the first component, once for the second, once for the third component. Let's find an antiderivative for f. And because we're a bit off screen here, let's just copy f down. Oh, yeah, copied a little funny. See if I can get it to look a little better. There we go. OneNote is so great for so many things, but formatting is maybe not one of them. Okay, so here's my function, and let's find an antiderivative for this function. So what is the integral f of t dt? Again, we're thinking of this just like essentially a Calc 1 or Calc 2 integral, but doing it 3 times. So if I integrate my first component, the integral of 3t is 3 halves t squared. And there's a couple ways that I can approach this next bit. But I'm gonna really think in terms of doing Calc 1 3 times, and I'm gonna say, plus something like C1, some arbitrary constant that's associated with the first component. So I'm going to call it C1 in anticipation that I'm going to have another arbitrary constant for the second component and another one still for the third component. What about the second component? I want to integrate e to the 2t. Well, that's going to give me e to the 2t. And I could do a substitution, or I could just kind of guess and check. And I see, okay, it's going to be e to the 2t. If I differentiate, that brings down a 2. That means I need a 1/2 to fix it. So 1/2 e to the 2t plus a different arbitrary constant. This one doesn't have to be the same arbitrary constant as in the first component. So we'll call this one C2. And then in the third case, integrate sine of t to negative cos of t. And again, plus C3. Or we could also realize that this is kind of a vector that has all of the t's in it, all of the interesting bits. And then kind of like plus a constant vector. We could actually rewrite it like that. We could see that just comes right out of the way that vector addition works. Where here, of course, the vector C is the vector with components C1, C2, C3. And we see that we just have kind of our variable vector part plus a constant vector. We could think of it that way also. We could think of the plus C as kind of coming into each component separately from each of those integrations that we did component-wise, or we could think of like a plus C vector being added on because our original function was a vector function. We could think of it either way. What if I want to compute a definite integral, something like integral from t equals 0 to 3 f of t dt? Well, what would I do here? Well, my fundamental theorem of calculus still applies, right? Because I know that this integral would be done component-wise, and I know that fundamental theorem of calculus applies to each of these components, these real valued functions. Maybe I should say to each of these components. So I can just take an antiderivative. Let me give this a name. Maybe I'll call this g of t. I can find that needs a vector bar. I can find an antiderivative, evaluate it at 3 minus that antiderivative evaluated at 0. And for g, I'll just choose the antiderivative where the constant vector is 0. That's the easiest one to use. So what's this going to be? This is going to be 3/2 times 3 squared, comma 1/2 e to the 2t, or e to the 2 times 3 e to the 6, comma negative cos of 3. That's g of 3, and then minus g of 0. Well, 0 squared is 0. We get a 1/2 e to the 0, just a 1/2. And a negative cos of 0, that's a -1. And putting these together, what do I get? For my first component, I get 3/2 times 3 squared, that's 27/2 minus 0. For my second component, I guess I get 1/2 times e to the 6 minus 1. And then for my third component, I get negative cos of 3 minus a -1. So that's 1 minus cos of 3. Any questions up to this point? I don't see anything in the chat. Any questions? Okay, so if your Calc 1 and Calc 2 is pretty fresh and pretty strong, this none of what we did here or none of what's, in the homework that are similar problems should be all that challenging. If you're finding these challenging, maybe ask yourself, is it the Calc 3 material that's challenging, or is it that, I don't quite remember what the, antiderivative of sine is, or, I don't quite remember how to do the chain rule super quickly or something like that. So if you're struggling on these, kind of ask yourself, is it the Calc 3 stuff or is it the Calc 1 and Calc 2 stuff, to know where to really focus your time. With this being such a condensed course, only 10 weeks, it's a lot of material for even a 15-week course in the fall or spring. Cutting it down to 10 weeks and being in the summer and there's other distractions and so on. It's really important to target your study time as best you can. Okay. We're moving through this more quickly than I expected to, so that's good. All right, so on to the idea of a unit tangent vector. So consider a vector function. We're going to start calling it r of t here. And we want to take a look at the derivative of r of t, d by dt, r of t. We could think of that derivative as the limit as h goes to 0 of r of t plus h minus r of t over h. And I want to draw a quick picture here. This picture is also in your book. It's maybe drawn a little bit more nicely in your book. But I want to draw a picture to kind of investigate what's going on with this difference quotient. So say we have some curve in three-dimensional space. It's not super important, how this curve looks from all perspectives. I know it's pretty hard to draw a single curve like this with a perspective that everybody would kind of agree what it actually looks like, but it's some curve in three-dimensional space. And I have two vectors. I can think of this curve being parameterized by the parameter t, and I have a vector r of t that I can imagine having an initial point at the origin and a terminal point at this point here, represented by the parameter t on the curve. I have another vector that points from the origin to the coordinate at t plus h. Let me actually move this this r of t bit here, move it to the other side. It's going to get in the way there. So that vector is r of t. I have another vector, r of t plus h. And then if I think, what is r of t plus h minus r of t? Well, I see that r of t, that vector that goes from the origin to the point on the line at t, plus this blue vector gives me r of t plus h. So r of t plus the blue vector equals r of t plus h, or r of t plus h minus r of t is this blue vector. right? Because r of t plus h, the the vector with kind of the lower slope as we're looking at it here, equals r of t plus the blue vector. So the blue vector is this vector pointing from the point at t to the point at t plus h. I could imagine that vector. I've kind of run out of colors at this point, but maybe I'll reuse black here. I could imagine that vector, if I continued it out, would look like a straight line connecting those 2 points. And that straight line would be kind of like a secant line that kind of cuts through the curve at 2 points. As h goes to 0, as we take this limit, as h goes to 0, this r of t plus h vector starts to look more and more like r of t. The vector in the numerator, the difference between those, is still going to be that straight line connecting those 2 points that are getting closer and closer together. The extension of that is still going to be a secant line, but it's a secant line that where its 2 points that characterize it are being squeezed together almost down to 1 point. And we should recognize this construction from the very beginning of Calc 1, that in the limit, we think that this secant line is going to turn into a tangent line. And indeed, that's what happens here. So just to kind of spell that out again, r prime is a vector, right? D by dt r of t. It's a vector that's tangent to the space curve represented by r of t. The lost my place here. Sorry. The analog to, it's the analog to the derivative from Calc 1. So r prime is the analog to the single variable derivative, and the straight line through this point is the tangent line to the space curve. So it's analogous to the tangent line from Calc 1 for our just real valued functions. So r prime basically gives us a direction vector for a line that is tangent to our curve, and then the point, the location information, so to speak, the point for that curve is the point of tangency. It quite often turns out that if you have a vector pointing in a certain direction, it's much nicer to have a unit vector in that direction when you're actually working with it. So quite often we're interested in finding the unit tangent vector, and that's t of t equals r prime of t over the length of r prime of t. So t of t is basically just r prime of t, but shortened or lengthened to make it unit length, to give it length 1. Any questions so far? We're flying through this much quicker than I thought we were going to, so it might be an early night tonight. We're most of the way through 13.1 and 13.2. Okay, so let's look at example 3 then. Example 3, we have a space curve r of t equals 2 cos of t, 2 sine of t, comma t. And we want to find the unit tangent vector and a parametric representation of the tangent line through the point root 2 pi over 4. Okay, so let's think for a second, what does this look like? Again, we haven't talked much about space curves. So what does this space curve look like? Well, from the perspective, kind of looking straight down, parallel to the z-axis, the projection onto the xy plane looks like 2 cos of t, 2 sine of t. On the xy plane, it looks like a circle of radius 2. So if instead of this being a t here, if it was, say, 0, what would happen as t goes from something like 0 to infinity or from minus infinity to infinity? We would just have a circle being traced out in the xy plane, and it would be traced out over and over and over and over again if the z component was just 0. But the z component's not just 0, it's t. So when t equals 0, we're at the point 2, comma 0, comma 0. We're at the point 2 on the x-axis and then 0 on y and z. And then as t starts to increase, again, if z was 0 and t was increasing, we would just be tracing out a circle in the xy plane. But if we started along that path and also take into account the fact that the z component is t, as t increases, we start to trace out that circle from the xy perspective, but z starts to increase as well. So we end up with something like this, where we have something that looks like a helix. Looks kind of like a slinky if you stretch it out a little bit. And we should make it all the way around in what, 2 pi. So that would be roughly 6.3 or so. We should be kind of back at a point that's directly above x equals 2, y equals 0, z equals 0. That's directly above that, but this should be the point 2, comma 0, comma 6.28 or so. So we'd expect this to be height something like 6.28. And then, of course, my most extreme point of the curve in the y direction is going to be above y equals 2. So it's a helix with kind of radius 2 in the x and y direction, and that moves vertically in that z direction. And this would be starting at t equals 0. Of course, if we wanted to plot the negative t's as well, it would just keep going, spiraling downwards. But this is t equals 0, and we traverse it in that direction for increasing t. We want to find a parametric representation of the tangent line at this point, root 2, comma pi over 4. We see that's going to be maybe, say, this point here, this kind of 45 degrees between x and y. And we're looking for the tangent line through that point. So ultimately, we need to find direction information and location information to determine a line. We have the location information. We'll call this P naught, root 2, comma pi over 4. So now we need direction information. What direction are we pointing? And that's what our unit tangent vector, or r prime, will give us. So let's start by finding t of t, our unit tangent vector. By definition, that's r prime over length r. And let's come off to the side here and look at what is r prime. Well, r prime is going to be negative 2 sine of t, 2 cos of t, and 1 in the third component. And then what's length r prime? Well, I get 4 sine squared t plus 4 cos squared of t plus 1, or just 4 times 1 plus 1 under the square root is square root of 5. So what's my unit tangent vector? It's 1 over root 5. Oh, missing one of my length bars there. 1 over root 5 times r prime. So there's my unit tangent vector. This is a vector that is pointing in the same direction as this tangent line here, and it has length 1. So this vector is t of t. So I found my unit tangent vector. Let me work on finding a parametric representation of the tangent line. So what do I need for the tangent line? I need location information and direction information. Again, the location information is pretty straightforward. We'll call it P naught, root 2, pi over 4. That's the point that we're given, the point of tangency, the point where we want to find the tangent line. And then what about the direction information? Well, for the direction we have, v can be really any vector that's in the direction of this red one here, that's parallel to the line. I could use t bar, right? I could use this up here, but that's got a square root of 5 in the denominator. That's just a little annoying to deal with. Do I really need the unit vector here? There are sometimes we really want the unit vector. But in this case, do I really need the unit vector? I don't really need it to be a unit vector here. I'll actually just use r prime. R prime, and importantly at this point is at t equals pi over 4. Right, just matching up the third components shows us that t has to be pi over 4. So my direction vector is going to be r prime at pi over 4. It's going to be a vector that's parallel to this red one that I've drawn on the picture here. This red one that I've drawn here is t of pi over 4 specifically. And that's going to give me what? -2 sine pi over 4, 2 cos pi over 4, comma 1. Or this is going to give me -2 root 2 over 2, 2 root 2 over 2, 1. Or this is negative root 2, 1. So that is my direction vector. And now I have a location vector and a direction vector. I maybe previously would have written something like r bar of t equals x of t, y of t, z of t, or something like that, or r. But we've kind of already used r, and we've kind of already used t. So we don't want to reuse those variables. So I'll just say parametric equations for the tangent line are x, y, and z. Well, these are going to be my x is going to be my x x coordinate plus the x coordinate of the direction vector, the x component of the direction vector, times my parameter. So it's going to look like root 2 minus root 2. And again, previously I would have said maybe t here, but t is already kind of taken up in parameterizing the space curve. I need a different parameter to parameterize my line. And so I'll just use s. I use the parameter s, a real number. What about y? Well, I take the initial point for y, which is also root 2, and then plus the y component of the direction vector times the parameter s, plus root 2s. And then same for z. Take the z naught, pi over 4, plus 1s, or just plus s. So this would be the parametric representation for my tangent line to this space curve at this point, root 2, pi over 4. Any questions on any of this?
Would you mind scrolling down to the bottom of this page?
Yeah, sure.
Appreciate that.
Yeah. Yeah, when I was writing these notes, this is my first time teaching this class over Zoom, and I anticipated this taking more time than this. But we got through basically all of section 1 and 2, except for a little discussion on space curves, and about half of the class. So it went a lot faster than I was anticipating. That sometimes happens. Often with Zoom, it goes slower than I'm anticipating. So I guess this is the better side to be on. So if they're okay, yeah, sure. Oh, so the domain of S is just real numbers. So this kind of thing just means the real numbers from minus infinity to infinity. Yeah. Yeah, exactly. So the reason I'll get to the length R question in just 1 second. The reason that we're using S instead is this curve is parameterized by T. So T's job here, when I say I'm interested in this point here, the point of tangency, we're saying, okay, that's the point associated with T equals pi over 4. But I also want to parameterize my line here. So it, like, kind of in a sense, this point on the line is associated with T equals pi over 4. So I need a different parameter to parameterize my line because, you know, I don't want these two running in lockstep with one another. I don't want to say something like somehow this point on my tangent line is associated somehow with, say, this other point on my space curve. That's not really what's happening. It's kind of like all of these points on the tangent line are associated with, in a sense, this single point on the space curve. So I need a different parameter, and I just chose to use S because T was already fulfilling this role, parameterizing the space curve, this helix. So we just needed some different parameter to parameterize our line. And if I wanted to give it a vector name, I wouldn't call it, R equals, again, because R is already fulfilling a role. It's the vector function for the space curve. I might call it, I don't know, you know, P or something like that. P equals XYZ, where those are my XYZ. Yeah. Yeah, so length R from up here. So this is we have our original R up here, 2 cos of t, 2 sine of t, t. Note that we then found R prime. So we were interested in finding a unit tangent vector. So we first found R prime, which was negative 2 sine t, 2 cos t1. And then that's what we're interested in finding the length of. So to find the unit tangent vector, we want the unit tangent vector to basically just be like R prime, but then make it a unit vector. So when I found the length down here, I actually found the length of R prime. So just a note on that. But how did I actually find this length? Well, if I have some vector V that's ABC, length V is root A squared plus B squared plus C squared. In essence, this is just by definition, or you could just kind of think of it. It's like if you apply Pythagorean theorem twice in 3 dimensions, you can come up with this formula pretty easily. So what is length R prime? What's going to be a square root of first component squared is 4 sine squared t, plus second component squared is going to be 4 cos squared t, and then third component squared is just 1. But from here, I can factor out a 4, and I get sine squared t plus cos squared t, which by Pythagorean identity is just 1. So it's just 4 times 1 plus 1. 4 plus 1 is 5. So that's where I got the root 5 from. Yeah, exactly. Yeah. So the sine and the cosine get squared, but also their coefficients get squared. Exactly. So that's where the 4 comes from. Super easy to mess that up. It's super easy to look at this and just like if you skipped out writing this step, I probably would even do this half of the time if I skipped this step. Forget to square those 2's and make it like 2 plus 1 and make it a square root of 3 or something like that. Just a funny mistake like that. But yeah, both of these factors get squared in each of those terms, and that's where that 4 comes from. The 4 is coming from the 2 squared, and then the 1 is just from this guy here. Yeah, sure. Yeah, you don't need to know too many trig identities for this course, but I'd recommend the Pythagorean identity, sine squared plus cos squared equals 1. I would recommend the double angle identities. So like sine of 2x equals 2 sine x cos x, cos of 2x equals cos squared x minus sine squared x. That obviously kind of, I don't know if you'd even necessarily call them identities or definitions, but things like sine, SOHCAHTOA, right? Sine is opposite over hypotenuse and so on. Yeah, that's probably most of what you would need to know. I don't think there's a whole lot that we do that uses really crazy trig identities. Um, there's something that's kind of on the tip of my tongue that just fell out of my head. Um, polar coordinates. Uh, I think probably if you're up to speed on these, if you if you're a little rusty on them, take 15 minutes or so, do a couple of problems in each of them. And but if you're up to speed on these, that probably will get you basically all of the trig you need to know in the course, or that you need to know going into the course. We'll encounter a few things here and there throughout the course, but that'll be stuff I think that you can kind of pick up pretty quickly along the way. But this is stuff that I would say is probably good to know at this point.